Imagine this. An astronaut in space throws a wrench forward, but instead of just the wrench moving forward, the astronaut begins drifting backward. Strange. Why this is happening? And now see this. When snooker ball strikes another snooker ball, the first snooker ball suddenly stops and the second one moves with the same velocity. Why this is happening? And similarly, you may have encountered with these two cores when they collide with one another, they move in backward direction. Why is that? All these are related somehow with conservation of momentum. So what is this conservation of momentum? In our today's lesson, we are going to study what is conservation of momentum, its examples, and the real-world applications of this conservation of momentum. Now, before going into the details of conservation of momentum, let's define what is collision. Here you see two cores, and these two cores are colliding with one another. And after the collision, these two cores, they are moving in backward direction. So we can define a collision is an interaction between two objects that made contact with each other. And collision results in a force applied to the two colliding objects. As these cores collide with each other, the red core is applying a force on yellow one, and the yellow core is applying a force on the red core. Is there a connection between collisions and Newton's third law? Here you see a boat and a person. A person is applying a force on the boat, and as a result, the boat is also applying an opposite reaction force on this person. And by the help of this reaction force, he is able to move and get out of this boat and reach to the ground. This is what we call the Newton's third law of motion, which says for every action there is an equal and opposite reaction. Just the reaction force is in opposite direction. That's why we need to put a minus sign. And also here you see two cores. One is red and other is yellow, and these two are colliding with one another. As the red core is applying an action force, the yellow core is also applying a reaction force on the red one. So the forces always exist in pairs. But now let's see this. Here you see two different trolleys. The first trolley is black with an extra mass on it, and the other trolley is without any extra mass. So this one is lighter and this one is heavier. And as I press the spring, then the black trolley is applying an action force on this lighter trolley, and that lighter trolley is also applying the reaction force on this black one. But as a result, we see that the lighter trolley is moving more faster. Why is this? Why does a lighter object flies away faster than the heavier ones? Here is the Newton's second law of motion, which says the acceleration of an object is inversely related with the mass. If the objects are heavier, then they have less acceleration. And if the objects are lighter, then they have more acceleration. As this trolley is lighter, so it has more acceleration. What is conservation of momentum? Let's assume we have two balls, one with mass m1 and it is moving with velocity v1 toward right, and another is with mass m2 and velocity v2, and that is moving toward left. And after some time these two balls collides. The red ball applies a force on green ball. Similarly, the green ball is also applying a force on red ball. So due to action and reaction, these two balls applies a force on each other, and after some time, after collision, they will move in opposite direction. The red ball is now moving toward left with velocity v1 prime, and the green ball is moving toward right with velocity v2 prime. As the masses are same, and we know that the momentum is the product of mass and velocity. So this is the initial momentum of the first ball plus, and this is the momentum of second ball. Similarly, after the collision, the momentum of first ball is p1 prime and the momentum of second ball is p2 prime. Now, the conservation of momentum says the total momentum before collision must be equals to the total momentum after the collision. So, before collision, the momentum of first ball is p1 and second ball is p2. The total means the sum of these two must be equals to the sum of the momentum after the collision of each ball. So we can write the statement of conservation of momentum, and it says in an isolated system the total momentum must be constant if there is no external force act on that system. So we can write m1 v1 plus m2 v2, which is the total momentum before collision, is equal to the total momentum after collision m1 v1 prime plus m2 v2 prime. Conservation of momentum is very important in physics because in all isolated system the momentum must conserve. As we discussed that the total momentum in any isolated system must be conserved, the momentum before collision must be equals to the momentum after collision. And in our first slide, we asked the question about astronaut. When he throws the object in space, he moves in backward direction. Why is that? That is, the initial momentum of astronaut is 0 before throwing an object. And as he throws the object is moving in forward direction with some velocity. So to conserve the momentum, the astronaut needs to move in backward direction. That's why he is moving in backward direction. So initially both have 0 total momentum. After the throw, the wrench has forward momentum, so the astronaut moved backward to conserve its moment, to conserve the total momentum. And another example was about snooker ball. Why the snooker ball stops as it hits the second ball, and second ball moves with the same velocity. This is because the first ball transfers all its momentum to the second during the collision. Before the collision, ball A has a momentum, and after ball A stops and ball B moves with the same momentum. So in this way, the total momentum is conserved because of this complete transfer to the second ball. But in this picture, you see that the first ball is still moving a little bit. So you cannot say that it is completely transferred, but almost it is all of the momentum is transferred to the second ball. Look at this rocket launch. As the engine fires, gases blast downward and the rocket moves up. Newton's third law of motion says that for every action there is equal and opposite reaction. The rocket pulls the gases downward and the gases push the rocket upward. Also, and this is also an example of conservation of momentum. The total momentum before the launch was zero as the rocket and the gases both were at rest. And after the launch, the momentum of this rocket and gases must be equal to zero. And that's why as the gases are moving in downward direction, the rocket is moving in upward direction to conserve the total momentum. And this even works in space where there is no air or ground. A 3 kilogram explosive object which is at rest on smooth plane fragments into two pieces of mass 1 kilogram and 2 kilogram. After an internal explosion, if the 2 kilogram piece moves due east at a speed of 3 meters per second, what is the velocity of the other piece? So here you see the object initially was at rest. As it explodes, the 2 kilogram fragment moves toward right and the 1 kilogram fragment moves toward left. And we choose the right side to be positive and left side to be negative. As velocity is a vector quantity, so we must consider the signs according to directions. We choose positive and negative. So let's start. Given we have total mass before explosion, and that is 3 kilogram, and the velocity, initial velocity is 0, and the mass of the first object is 1 kilogram. Similarly, the mass of second object is 2 kilogram. The velocity of second object is toward right, toward east, and that is 3 meters per second. Similarly, what is required? We need to find what is the velocity of the other piece. What is other piece? This 1 kilogram. So the velocity of 1 kilogram mass, by conservation of momentum, we can write the total initial momentum must be equals to the total final momentum. And as the total initial momentum is the total mass times the velocity of this object before explosion, and as we know that the velocity was 0, so this term will be 0, is equals to m1 the mass of the first fragment, and V1 the mass of the second fragment, plus the mass of second fragment to the velocity of second fragment. So the sum of these two must be equals to this one. So as the initial momentum is 0, so final momentum must be equals to 0. So by using this, we can write the values. We do know all other values except V1. So we can rearrange and get V1 is equals to minus 6 meter per second. And here negative sign shows us that the velocity of 1 kilogram is in opposite direction to the velocity of the 2 kilogram mass. Dear students, here's your homework with on page 168 and 69, problem 20, 21, and 25. Thank you very much.